this lecture, we will explore some classic puzzles, many of which have been driving people crazy for centuries. On the surface, they seem very different: sliding blocks, jumping pegs, and blinking lights, but they do have some common features, and I'll mention one of them here. Although none of these are what you'd call number puzzles, we'll see that each of them deals with odd and even numbers in their solution or analysis. I thought of calling this lecture "Odd Puzzles Can Be Even More Interesting," but I changed my mind. Now let's get started. Let's begin with a classic puzzle. You might even call it the Rubik's Cube of the 19th century. It's called the 15 puzzle, and I'm sure you've seen one of these before in some form or another. Sometimes there's a picture that gets scrambled up in which you have to restore the picture. In its classic form, you have the numbers 1 through 15 in a 4x4 square and a blank space that allows the squares to move. Now, here's an electronic version that works on the iPad. You start with a randomly scrambled position, and your goal is to get it back to the original order. I'll say more about the mathematics and history of the puzzle later, but let me first teach you how to solve the puzzle. The solution is pretty intuitive. You basically get the numbers in the right place, one at a time, with just an occasional twist. Let me first outline the solution method for you, and then we'll solve a random puzzle. Starting from a random position, you first want to move the tiles 1 and 2 to their goal positions. That's pretty easy. Next, you want to bring 3 and 4 to their positions. But if you bring the 3 here, then you probably aren't going to be able to get the 4 into its proper place. So instead, you bring the 3 here and the blank here, right? So you have the 3 here, the 4 here, and the blank here. After that, we can bring the 3 and 4 to their proper places, like so. The numbers 1 through 4 are now in their final positions, and they won't move for the rest of the puzzle. The next row is pretty much the same. First, you bring the 5 and 6 to their proper positions. Then bring the 7 over here and the 8 over there with a blank over here, and then you bring them home, like so. The first 2 rows are finished, and you'll never need to touch them again. Now we're starting to run out of maneuvering room. The next tiles we place are not 9 and 10, but 9 and 13. We want to bring them here, but if we start by putting the 9 there, we won't be able to squeeze the 13 into the corner. So first, bring the 9 and 13 next to each other, like so, then bring them home. Almost done. Next, we want to move the 10 and 14 to their final positions. But to do that, we first need to bring them here and then to here. Finally, we're just left with the 11, 12, and 15 in some order. If the original puzzle was solvable, then they can simply be rotated to reach the goal position. Like so. World chess champion Bobby Fischer was able to do this puzzle consistently in under 25 seconds. I'm happy if I can finish it in under 2 minutes. So let's give it a try. Okay, here we go. I'll talk through it as I do the problem. Okay, 1 is already in the right position, so I first have to bring the 2 over like so. Okay, next we want to bring the 3 and the 4 over to there. Okay, the 3's where it needs to be. Now let's get the 4 underneath it, like so. 3, 4 are done. Okay, now let's move that 5 up where it wants to go. Okay, well, we got to get the 6 next to it. All right, let's take the long way to get there. All right, now up. Okay, there we are. Oh, the 7's where it needs to be. That's great. Let's put the 8 underneath it. Now we have 7 and 8. Now we need to get 9 and 13 next to each other. There they are. We can now slide them to where they belong. Good. Finally, we need to get the 10 and the 14 next to each other. Let's space them out here first, and now we can put the 10 and 14 like so. Great, 11, 12, 15. We're done. Hey, I broke 1 minute. That's a personal best. The 15 puzzle was invented by Noyes Chapman, a postmaster from New York, and later popularized by the puzzle maker Sam Lloyd. Lloyd offered $1,000 to anyone who could solve the following puzzle. Starting from the original 15 puzzle position, can you rearrange the tiles to reach this position where tiles 14 and 15 have been swapped? Lloyd's money was safe because it turns out that this puzzle has no solution. The reason has to do with even and odd numbers. Let me explain. The numbers 1, 2, and 3 can be arranged in 6 ways, right? 3 factorial ways. Let's look at the arrangement 1, 3, 2. So I have the cups here 1, 2, 3. Let's look at the arrangement 1, 3, 2 like so. Notice that we can bring it back to the original order by performing one swap, right? I go from 1, 3, 2 to 1, 2, 3 in one swap. Whereas if I started with the arrangement 2, 3, 1, then that's going to require 2 swaps. Like I could swap the 1 and the 2, then the 2 and the 3, like so. Here's a table of all 6 arrangements. Mathematicians call these permutations, along with the number of swaps needed to bring them back to the original order. Here they are. Now let's look at 1, 3, 2 again. Okay? Now, there are a lot of other ways we can use swaps to bring it back to the original order, right? So like for instance, I could go, I could swap, do one move here, and then another move here, and then finally another swap here, okay? That took me 3 swaps. Now, there are other sequences of moves that take 3 swaps, or 5 swaps, or 7 swaps. What's interesting, or should I say what's odd, is that no matter how hard you try, you can't straighten out 1, 3, 2 in an even number of swaps. The number of swaps has to be an odd number. So we call 1, 3, 2 an odd arrangement. Looking at all 6 arrangements again, we can label them as odd or even as follows. Notice half of them are even, half of them are odd. So just like every number can be labeled as odd or even, every arrangement of objects, whether it be 3 objects, 16 objects, or whatever, can be labeled as odd or even. So to bring your arrangement back to its original order, an odd arrangement requires an odd number of swaps, and an even arrangement requires an even number of swaps. So let's go back to the 15 puzzle. Okay, here's a brand new arrangement. Every position is some arrangement of 16 objects, right? Namely the numbers 1 through 15 and the blank. Now, Lloyd's puzzle is clearly an odd arrangement since it's just one swap away from the original order, right? Just swapping 14 and 15 gives you Lloyd's arrangement, so that's clearly an odd arrangement because 1 is an odd number. So if there's a solution to Lloyd's puzzle using legal moves, it must be an odd number of legal moves. But notice this. Every legal move is actually a swap that involves the blank square and an adjacent square, right? As I'm moving this, you can really think of every move as a swap with the blank tile and some other tile. But notice that the blank square begins in the lower right corner and it ends in the lower right corner. Thus, the blank square must travel an equal number of moves to the left as moves to the right. And the blank square has to make an equal number of up moves as down moves. So the total number of moves, all of which are swaps, must be an even number. So in order for a puzzle to be solvable, it has to come from an even arrangement. Thus, Lloyd's problem here is impossible since it came from an odd arrangement. Now, as it turns out, we can solve any position that comes from an even arrangement of the numbers 1 through 15. So, for example, if we swapped 14 and 15, and also say 4 and 9, then the algorithm we learned will successfully solve it. But if we start from any odd position, then our process would eventually lead us to the Lloyd position, and we would be stuck. Now, we saw earlier with the arrangement of 3 numbers that half the arrangements were odd and half of them were even. And that's true in general. So if someone physically removed the tiles of a 15 puzzle, okay, just shook them out here and put them back at random, then there would only be a 50% chance that the puzzle would be solvable. In fact, when I was preparing for the course, one of the apps that I purchased had that very flaw. Half the time, the puzzle it gives you is unsolvable. How frustrating. Some apps, like the one we use here from the company AppAnnex, are smarter and only give you solvable puzzles. By the way, how can you tell if a given arrangement of pieces will be solvable or not? After moving the blank square to the bottom right-hand corner, you can determine if an arrangement is even or odd by counting for each square how many lower numbered squares come after it. If it has an odd number of smaller numbers that come after it, we call that square an oddball. At least I do. A legal arrangement has to have an even number of oddballs. So in the goal arrangement, there are no oddballs. It's never the case that a lower number comes later than an earlier number. And so since 0 is an even number, then that's fine. This is a legal arrangement, of course. Whereas with the Lloyd arrangement, we have one oddball, namely the number 15. So this arrangement's impossible, right? Because after 15 comes 14. That's one number that's smaller than it. Here's a random position from my app. Now, the number 12 has all 11 of its smaller numbers coming after it, right? So that makes 12 an oddball, right? Whereas, let's look at the number 6 in the diagram here. What numbers come after it? 11, 3, 4, and 14. 3 and 4 are smaller than 6, so 6 has an even number of smaller numbers coming after it, so 6 is not an oddball. The number 10 has 7 of its smaller numbers coming after it, so it's an oddball too. You can check for yourself that none of the other numbers are oddballs. Since this puzzle has exactly 2 oddballs, it is solvable. But if we swapped any 2 of those numbers, then we would have an unsolvable puzzle. Now in the 15 puzzle, you could tell that you were making good progress towards a solution as more and more of the squares were brought to their proper place. But that's not always the case with puzzles, especially electronic ones like we have in our next example. I have here a 3x3 box of lights. At the start of the game, some of the lights are on and some of the lights are off. Actually, these lights are all buttons, and we can label the buttons as numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. So this position here, you could say, has buttons that are lit, buttons 2, 3, 5, and 8. Those are on, and the rest are off. Your goal is to turn off all the lights by pressing the right combination of buttons. Now, there are 3 types of buttons. Corner buttons, buttons 1, 3, 7, and 9, edge buttons 2, 4, 6, and 8, and the middle button, button 5. Pressing a corner button will toggle the corner and the 3 surrounding lights. For example, pressing button 1 will toggle these 4 lights, the lights in cells 1, 2, 4, and 5. Notice right now we have off, off, on, on. Well, after I press button 1, it's going to look like on, off, off. And if I press button 1 again, it's going to bring us back to the original position. Whereas pressing button 3 toggles lights 2, 3, 5, and 6. Pressing button 7 will toggle these 4 lights, and button 9 will toggle those 4 lights, like so. Pressing an edge button will toggle the edge and 2 of its surrounding neighbors. For example, pressing button 2 up here will toggle the lights in cells 1, 2, and 3. So right now, the first row looks like off, on. Then after pressing button 2, it looks like on, off, off. The other rows don't change, okay? Pressing button 2 again would take us back to where we were. Similarly, button 4 toggles lights 1, 4, and 7. So these lights get toggled. Right now, they're all off, and then after I press button 4, they're all on. Pressing 4 again brings us back. And similar rules apply for pressing button 6, which toggles these 3 lights, and pressing button 8, which toggles those 3 lights. Finally, pressing button 5, the middle button, toggles the middle and the 4 edge lights 2, 4, 6, and 8. So pressing 5 would take us from here to there and back again. So those are the rules. Our goal is to press a sequence of buttons so we go from the initial position to the position where all lights are out. Poof! Hopefully using as few buttons as possible. The solution is far from obvious. Before I give it to you, let me ask you another question. When pressing the buttons, let's go back to our original position, does the order matter? For example, if I take a position like this one and press the buttons 1, 2, 3, 4 in that order, will I get the same position if I press the buttons in a different order, say 2, 4, 1, 3? What do you think? Same or different outcome? The answer is not clear. To clarify this situation, it's time to introduce what mathematicians call mod 2 arithmetic. With mod 2 arithmetic, there are just 2 numbers, 0 and 1. For the most part, addition works in the usual way. 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, but 1 plus 1 is not 2, since the number 2 is not in our original number system. We only allow 0 and 1. As a result, with mod 2 arithmetic, we have 1 plus 1 equals 0. One way to make sense of mod 2 arithmetic is to think of 0 as representing any even number and 1 as representing any odd number. Then the mod 2 addition table is really just saying even plus even is even plus odd is odd, and odd plus odd is even. Let's see how mod 2 arithmetic comes in handy with this puzzle. First of all, every position can be represented by a vector of zeros and ones, where 0 means that a light is off and 1 means that a light is on. For example, our beginning position here would have vector representation 0, 1, 1, 0, 1, 0, 0, 1, 0, where we have a 1 in positions 2, 3, 5, and 8. Now, each button can also be represented by a vector. For example, pressing button 2, which toggles the lights in positions 1, 2, and 3, right? Pressing button 2 affects lights 1, 2, and 3. I claim that pressing button 2 is just like adding the vector v2, which consists of 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay, so let's see that in action. For example, if we take our beginning position and press button 2, we get a new position where lights 1, 5, and 8 are on. Notice if we take the vector representing the original position with lights with ones in positions 2, 3, 5, and 8, and I add the vector v2, which has ones in positions 1, 2, and 3, and I do that addition mod 2, of course, then the new vector b plus v2 will have 1s in positions 1, 5, and 8, just like our lights. We have lights in the 1st, 5th, and 8th position. Similarly, pressing button 1, which toggles lights 1, 2, 4, and 5, is equivalent to adding the vector v1 with 1s in the 1st, 2nd, 4th, and 5th position. And similarly for the other buttons. By the way, we've seen that pressing a button twice in a row leaves a position unchanged, right? But we can also see that from vectors. For instance, if we press button 1 twice, that's just like adding the vector v1 plus v1, which is the vector of all zeros. So pressing a button twice in a row literally adds nothing to your position. So now that you see that pressing a button is the same as adding one of the 9 vectors, v1 through v9, I'll ask you again, does the order that you press the buttons matter? For instance, if you press button 1, then button 2, is that the same as pressing 2, then 1? Well, pressing 1, then 2 is the same as adding the vector v1 plus v2. But notice that's the same as adding v2 plus v1. So what that tells us is the order doesn't matter. And that's true for any 2 buttons. This fact was not at all obvious, at least to me, until we used vectors to represent the buttons. All right, so let's hear it for vectors and Mod 2 math. And by the way, since order doesn't matter, no solution would require you to press the same button twice, right? I mean, you'd never press a button twice in a row. You wouldn't have to do it. So you wouldn't press them far apart either, because you could rearrange those button presses so that they were twice in a row. So, in other words, if a puzzle has a solution, then it has a solution where every button is pressed at most once. Okay, but how do we find a solution? Strictly speaking, this is a problem from linear algebra, the mathematics of vector equations. Starting from your beginning position, represented by the vector b, you need to add some of the vectors v1 through v9 to reach the vector of all zeros. The vector of all zeros is the position where all lights are off. Now, a linear algebra student can take the initial vector and the button vectors and find a unique solution by solving a system of equations. But let me show you a quick way to solve this problem in your head without the need to write down a single equation. Recall that when we solve this puzzle, the order that you press the buttons does not matter. So since it doesn't matter, I will always solve the puzzle in the following order. I will first decide on the edge buttons, then I'll decide the corner buttons, and then finally I'll decide the middle button. Now you'll admit that if I can do steps 1 and 2 correctly, then the third step, deciding on the middle button, is trivial, since I'll either be done with the puzzle or I'll have to press button 5. For instance, in the original puzzle here, once I choose the correct edge and corner buttons, bam, 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 all the lights are off and there's nothing left to do. If the lights were not out, here let me press button 5, then we'd be in this position and we'd only have to press button 5 to finish, like so. But how do we decide the edges and corners? Okay, let's look at the corners. Now I claim that if I can solve the edges, then the corners are also easy, extremely easy. Here's why. After I press the correct edge buttons, the only buttons remaining for consideration are 1, 3, 5, 7, and 9. Now, let's look at corner number 1 here. Which of the remaining buttons will affect light 1? Now, button 1 will definitely toggle it, but none of the remaining buttons will. Right? Button 3 doesn't affect that, number 5 doesn't affect it, 7 and 9, none of those affect it. So if light 1 is on, then you're going to have to turn it off, right? Because in the end, we want everything off. So if it's off, leave it alone. If it's on, you must press it now. The same is true for the other corners. So in step 2, you simply turn off the lights at every corner. So in the original position, once I correctly choose the edge buttons, bam, bam, then the corners are easy. The only lit corner is corner 7. So when we press it, we're done. So if we can figure out the edge buttons, then we're home free. But how do we figure out the edge buttons? For example, how do we decide whether or not to press button 2? To do this, we look at the rectangles surrounding button 2. Now consider the following question. For each of the buttons 1 through 9, how many lights are toggled inside the rectangle? I've written the answer for each button here. For example, button 1 toggles these 4 lights, all of which are in the rectangle. Button 5 toggles 5 lights, but only 4 of them are in the rectangle. That's why we have a 4 there. Button 8 toggles 3 lights, but none of them are in the rectangle. That's why the 0's there. Now, do you notice anything interesting about button 2? It toggles 3 lights inside the rectangle, and it's the only button that toggles an odd number. In the end, we want no lights on in that rectangle. So here's what we do. Count the lights in the rectangle surrounding button 2. We see that in our position here that there are presently 3 buttons lit inside of that rectangle, right? That's an odd number. In the end, we need to have an even number. We need to have 0 lights lit in that rectangle. So, since all the other buttons will change the number of lights in that rectangle by an even amount, if we want to get from an odd number of lights in that rectangle to an even number of lights in that rectangle, we must press button 2 now. The other edge buttons can be determined in a similar way. For example, with button 4, we look at the rectangle that surrounds it and see that right now it has 3 lights lit inside of that rectangle. Since we want to have an even number, we're going to have to press button 4 to change the parity of its rectangle from odd to even. On the other hand, when I look at the rectangle for button 6, we see that it has 4 lights lit. That's an even number, so we leave button 6 alone. How about button 8? Tell me what we should do here. For 8's rectangle has 2 lights lit, right? That's an even number, so do we press it or leave it alone? It's even, so we'll leave it alone. So which of the 4 edge buttons are we going to press? Buttons 2 and 4. Let me do so quickly. Bam, bam. All right, all that we're left is pressing button 7. And we're done. Let's do one more example. Okay, create a random position. That looks nice. How do we do this? First, we're going to decide the edge buttons, then we'll do the corner buttons, and then we'll do the middle buttons. To do the edge buttons, we have to look at the rectangles for buttons 2, 4, 6, and 8. Button 2 has a rectangle that looks like this, and I see it has 4 lights lit. So we're going to leave button 2 alone. Rectangle 4 has 4 lights lit. Okay, we'll leave that one alone. The rectangle for button 6 has 3 lights lit, so we're going to want to press 6. And the rectangle for button 8 has 4 lights lit, so we're going to leave that one alone. So the only edge button we need to press is button 6. So let's do that. Okay, next we press the corners that are lit. I only have 2 lit corners. We'll do that. Bam, bam. Well, we're not done yet, so that means we have to press the middle button. When we do that, we're done. The last puzzle I'd like to do was a favorite of mine of my childhood called Peg Solitaire. It's typically played on a board that looks like a giant plus sign. Every spot, except for the central one, is occupied by a peg or sometimes a marble. Pieces can jump over other pieces, horizontally or vertically, provided there's an empty space on the other side. and the piece that's jumped over is removed from the board. For example, in this puzzle, our first move can either be a horizontal jump, like this, or it could be a vertical jump, like that. The goal of the puzzle is to jump your pieces in such a way that all you're left with at the end is one piece, preferably in the middle of the board. In fact, one puzzle maker says that if you can end up with one piece, you are outstanding. And if it's in the middle of the board, then you are a genius. Let me first show you a quick solution to this puzzle. Then I'll show you that, contrary to the puzzle maker's claim, ending up with one peg outside the middle hole should not make you outstanding. Okay, here's the solution to the puzzle. Begin by making our initial move towards the center, or as I like to say, bottoms up. Now, here's the mnemonic I use to clear most of the pegs from the board. As a professor, you write lots of papers, especially early in your career as you seek tenure and promotions. And no matter how many papers you've written, it seems that there's always one more right up left if you want to move up in the profession. So repeat after me. Right up left, then move it up. Okay? And we're going to repeat this 4 times. So we go right, up, left, and then move it up. It is this peg here. How do we move it up? By bringing this down and jumping up. All right, if you didn't get it, that's okay. We're going to do it 3 more times. I rotate the board, and one more time we go right, up, left, and move it up, just like so. All right, we rotate again. Right, up, left, and move it up. Okay, last chance. Rotate, and we have right, up, left, and move it up. And when we do, and I'll rotate it one last time, we have a house, right? Or a Space Invaders character, whatever you'd like. Now we're going to clear the rest of the pegs by going to the attic in the house, and this piece is going to do a grand tour all around and annihilate most of the pegs. Here we go. We're going to jump here, and then 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 here, ending up in this T formation. And now the puzzle's pretty easy to solve, right? We jump this way, that way, this way, and we're done. Got it? You are now officially a genius. Curiously, as we're about to see, the middle square is practically the only place that a single peg can end up. I'll prove it to you by labeling our board with the symbols X, Y, and Z, like so. Now I'm going to give you some simple rules for adding the symbols X, Y, and Z together, and you'll see why we want to do this in a minute. Now here's my addition table. Take a look at it. Notice that when we add 2 letters together, we get the third one. For instance, X plus Y equals Z, or Z plus X equals Y. When you add a symbol to itself, you get 0. For instance, X plus X is 0. And as usual, adding 0 to something leaves it unchanged. For instance, 0 plus Y is Y. Now what do X, Y, and Z represent? When we did Mod 2 arithmetic, we saw that 0 and 1 could be thought of as even and odd numbers. With X, Y, Z arithmetic, we think of each symbol as representing a pair of even or odd numbers. Here, X would be the even-odd pair, Y is odd-even, Z is odd-odd, and 0 is even-even. Then everything is nice and consistent. For example, the statement X plus Y equals Z really says even odd plus odd even equals odd odd, which makes sense, right? For instance, 2 1 plus 5 2 equals 7 3. And a statement like x plus x equals 0 is saying that even odd plus even odd is even even. Anyway, trust me when I say that the symbols x, y, z, and 0 form a consistent mathematical system called the Klein 4 group. I'll point out one last useful fact. I claim that x plus y plus z is 0. We can verify this because x plus y plus z is the same as z plus z, which is 0. Okay, so how do these symbols help us understand peg solitaire? For any peg solitaire position, we define its signature to be the sum of the symbols of all of the occupied squares. For example, the T formation that we saw earlier has signature x plus y plus z plus x plus z. That's 0 plus y, which is y. Okay, how about the house position? Exploiting the fact that x plus y plus z is 0, I see 3 xyz triples, each of which sums to 0, so we could ignore those. So the signature here is x plus z, which is y. What about the signature of the original position? If we replace each xyz with 0, we get massive cancellation, and all that we're left with is x plus z, which is y. It seems as if every position has a signature of y. Do you see why? Look at the XYZ pattern on the board, okay, this one here. Notice that every 3 consecutive squares contains an x and a y and a z, like say in this position here, or here, or there. Every time you perform a jump, you're replacing 2 pegs from occupied squares with 1 peg from an unoccupied square. For instance, if you jump from x over z, you must land on a y. But that won't change the signature at all, since x plus z is equal to y. Consequently, the signature of the board will never change. And since the signature started at y, it will forever be y. Thus, if we can reduce the puzzle down to a single peg, then it must be on a square with label y. And yet, not every square with a y is a possible ending point for a single peg. Now, why is that? For example, I claim that we cannot wind up with a single peg on this square. Now, why is that? Because if we could, if there was a sequence of moves that where a peg ended up on that square, then by symmetry, we could also have performed a sequence of moves that would allow a single peg to finish on this square. And since it's impossible for a single peg to finish on a z square, we can't finish on that y square either. By the same logic, you can disqualify most of the other y squares as landing spots except for these 5. And yet, how could the final peg land in one of these end squares? How could we get something to end up in this square? Only if the last 2 pegs were situated like this. But if that's the case, then those pegs could have just as easily jumped to the center. And if getting to a peg in the center earns you a genius rating, you'd be foolish to jump the peg anywhere else. So, why should a solution of 1 peg away from the middle earn you an outstanding rating? I don't know. A couple of years ago, I was at a friend's house and I noticed a puzzle he had in his living room that he had picked up in his travels. It looked like peg solitaire, but it had 4 extra squares on it. Just like in the original puzzle, all the squares were occupied except for the middle square. My friend said that he was never able to solve the puzzle. Then he said, "Hey, you're a mathematician. Maybe you can figure it out." I brought out a piece of paper and labeled the board with X's, Y's, and Z's, just like before, with the 4 new squares included. Let's see why my friend was having such trouble. It was still the case that every 3 consecutive squares in a row or column had an X, a Y, and a Z in it, so the signature would not change. So what is the new signature? Well, previously the signature was Y, so the new signature, which has these 4 new squares on it, would be Y plus X plus Y plus Z plus Y. And since Y plus Y is 0 and X plus Y plus Z is 0, the signature of the new board is simply 0. Consequently, it would be impossible for a single peg to land anywhere, since that would change the signature to X or Y or Z. Hence, the puzzle was impossible. My friend was grateful, and my reputation was saved. In this lecture, we've seen how mathematics plays an interesting role in solving and understanding various puzzles. Although the puzzles we considered were very different, their solution methods had some common elements, which apply to many other puzzles as well. One thing to look for when solving a puzzle is what computer scientists sometimes call a macro. A macro takes rules of your game and looks for efficient combinations of those moves that help you solve your problem. In the 15 puzzle, once we found an efficient way to solve the top row, we could repeat that process for the second row, and the last 2 rows were finished in a similar fashion. And in Peg Solitaire, we found that the right up left and move it up macro could be performed 4 times and reduce our puzzle to a much more tractable problem. Another common theme that appeared in all of our puzzles was the exploitation of parity. Now, for instance, in the 15 puzzle, we saw that there were odd arrangements and even arrangements. The analysis of our electronic game was all about mod 2 arithmetic, and even with Peg Solitaire, we found that the symbols X, Y, and Z and 0 represented pairs of even or odd numbers. With games of chance, we spoke often about determining the best odds and trying to break even, and so it is with puzzles that it often pays to look at odds and evens too. Let me end with one last impossible puzzle frequently found in restaurants while waiting for your pancakes. It's Peg Solitaire played on a triangular board like so. Starting with one empty hole on the top, your goal is to eliminate all pegs but one, preferably left in the top hole. Here's the solution along with my mnemonics. Now, after our initial jump, okay, that is from here to there, the next 4 moves will all use this point somehow. Now, after this sideways jump, my daughter said that this sort of looks like a snail. Okay, so now the snail will lose its tail on the pail. All right, what do I mean by that? All right, so the snail loses its tail on the pail. And now we aim for an A-, and I'll tell you what I mean by that in a moment, by jumping from the corner followed by a double jump. So I jump here and a double jump, jump, jump. And now I have an A minus the top 2. All right? Now, finally, we create a diamond by jumping up from here, up from there, and now we clear the rest. 1, 2, 3, and we are done. Time for some pancakes. In our next lecture, we'll take on perhaps the most famous puzzle of all time. So be there or be square, or maybe I should say, be there and b cubed.